Good day, grade 11 STEM students. Welcome to the HP Classroom. In this video, we will be talking about sigma notation. So our subtopic for today is about writing and evaluating sums in sigma notation. So, summation or sigma notation is a convenient and simple form of shorthand used to give a concise expression for a sum of the values of a variable. At this moment, we'll need to define what is sigma notation. So, we will let f of I be an expression involving an integer I. And the expression is expanded in this form of series, f of m plus f of m plus 1 plus f of m plus 2 until f of n, which can be compactly written in sigma notation, and we write it as the summation of f of I from I is equal to m, from m to n. And we will discuss its parts. So, this symbol right here is a summation sign, or the Greek uppercase letter called sigma. So this is the symbol for the series that we need, the series. So f of I is what we call the typical element, or simply the expression involved in the series, which is determined by our lower limit and upper limit. So index of summation is the variable in the typical element, and the starting point is the lower limit of the summation, which is denoted as letter m. And sometimes, or more often, it starts with 1 until a certain number, and that is our stopping point or the upper limit of summation. And it depends upon what values for m and n we will have to get the sum. So for index of summation, it can be changed. It's not always letter I because it is a variable. It depends upon the problem on what variable are we going to use. So that's it for the parts. And in order to read this notation, so we will read it as the summation of f of I from I is equal to m to n, or from m to n. For the first set of examples, we need to expand each equation and simplify if possible. So these are the functions that we will expand according to the lower and upper limits. So we will now expand and get the sum and to simplify. So we have summation of 2 raised to I from I equals 0 to 5. So to expand, we'll start from 0 to raise to 0 plus, we will add by 1 until we reach 5, plus 2 raised to 1, plus 2 squared, plus 2 cubed, plus 2 raised to 4, plus 2 raised to 5. So we will stop right there, and then let's evaluate. 2 raised to 0 is 1, 2 raised to 1 is 2, plus 2 squared is 4, plus 2 cubed is 8, plus 2 raised to 4 is 16, and 2 raised to 5 is 32. And their sum is equal to 63. So that's the answer for the first example. For the second example, we have summation of a sub I from I equals 1 until n. So to expand, we need to simply change our i's with the given values for lower and upper limits. So a will start with a sub 1 plus a sub 2 plus a sub 3. So we do not know when this will end, so we will put ellipsis and then add, and we will until we reach a sub n. So in this case, we cannot get the sum for this sequence, so we will stop right there. Our third example is the summation of 2i plus 3 from I equals 2 to 4. So we will expand this expression or this summation by replacing the values 2 to 4. So we have 2 times 2 plus 3 plus 2 times, add by 1. So we have 2 times 3 plus 3 plus, we will add again by 1. So we have 2 times 4 plus 3. Then after evaluating this, we have 2 times 2 plus 3 is 7, 2 times 3 plus 3 is 9, and 2 times 4 plus 3 is 11, which sums up to 27. So that's the sum of our series. For the last example, we have the summation of square root of n over n plus 1. We will expand this equation and see what will happen. So we have square root of 1 over 1 plus 1 plus the square root of 2 over 2 plus 1 plus the square root of 3 over 3 plus 1 plus the square root of 4 over 4 plus 1 plus square root of 5 over 5 plus 1 and until 6 square root of 6 over 6 plus 1. So let's simplify. So the square root of 1 is 1 and over 1 plus 1 is 2. We will rewrite square root of 2 and 2 plus 1 is 3. Rewrite square root of 3 over 3 plus 1 is 4. Square root of 4 is 2 and 4 plus 1 is 5, so 2/5. We have square root of 5 over 6 and square root of 6 over 6 plus 1 is 7. After adding in a scientific calculator, so we get the sum of approximately equal to 2.53. So since our sum is not exact, we will let our answer be this. In the second set of examples, we need to write each expression in a sigma notation. So these are the following series that we need to transform into a sigma notation or in a summation form. So we need to look for, first and foremost, we need to look for the typical element, put some index of summation, and look for the lower and upper limits. So if we will let n be the first term, second term, third term, fourth term, until a certain value for the stopping point, which is also n. So in this example, these two n's are different. So the n on the left side is for the index of summation, and the n on the right side is for the stopping point. So we need to look for its typical element. We will examine the behavior of the series when it become 1, when this become 1/2, 1/3, 1/4, until 1 over 100. So you can observe that the numerator is always 1. And the denominator behaves as n increases. So we can say that our summation is equal to summation of 1 over n from n is equal to 1 until 100. So I will rewrite this here. So we have 1 over n from n equals 1 until 100. So it's just a coincidence wherein we use n as the index of summation and our stopping point. So that is our answer. For the second series, we have a sub 2 plus a sub 4 plus a sub 6 plus a sub 8 until a sub 20. So again, we need to look for the typical element, the lower limit, and the upper limit, or the lower and upper boundaries or bounds. So this time, we will use I as index of summation, but you can use any variables that you want. So we will write this as 1, 2, 3, 4 until n, or the stopping point. As we can see, this is a finite series. So all of them starts with a, or they have a base of a. And when does it become 3? When does it become 4? When does it become n equals 20? So we can see that they are always multiplied by 2 to get the subscript. And then we'll just put I. From 1 until 20 divided by 2 is 10. So that's the final answer. So we have the summation of a sub 2 I from I equals 1 until 10. For the third, I will just box it here. For the third example, this is a tricky example because it involves positive and negative signs. So we need to look again for the function or the typical element. This time we will let k as our index of summation, and we will still look for our lower and upper bounds. We can see that there is an interchange of signs of negative and positive in our series. So we have k. We'll put 1, 2, 3 underneath the terms. And we can see that it involves negative 1. And then we will multiply it by the number of terms, which is kth term, which is 1, multiply it. We will multiply negative 1 by 2, by 3, by 4, and negative 1 by 5 until we reach 25. Negative 1 times 25. However, when will we get the positive sign? During even terms or even numbers. So we simply raise it by the number of terms also. So raise it by until 25. So we can generalize it into the form negative 1 raised to n, raised to k, I mean. Okay, again, we will write it. Negative 1 raised to k times k. Then we will put this typical element into this box. So we have negative 1 raised to k times k. You just need to be observant. So we have k raised to from k is equal to 1 until 25. You need to be observant for each series and how it behaves. And you can always manipulate it in different techniques, as long as each term will be equal to what your summation is. Once you have replaced the values. So the last example is very easy because we can already see the relationship from the numerator and the denominator. So again, we need to look for the typical element. We let k be our index of summation, and we will look for the lower and upper bound or upper limits. So again, we can see that this is a finite series, and 1 is our numerator. So let's see the behavior of the summation if we will start with k equals 1, or our starting point be equal to 1. So 1, 2 becomes 2, 3 becomes 4, 4 becomes 8 until 128. But we can see a pattern here that we raise the number of k values up, raise 2 by the number of values. So we have 2 raised to k. Because 2 raised to 1 is 2. 2 raised to 2 is 4. And 2 cubed is 8. However, our first term needs to be 1, not 2. So, to become 1, we need to raise 2 by 0, so it becomes 1. So, we need to subtract this with 1. So, we have 1 over 2 raised to k, 2 raised to k minus 1. From 1 until our last term, which is 8. So that's our final answer. We have the summation of 1 over 2 raised to k minus 1 from k is equal to 1 until 8. Then we will just box here for a while, and we can observe that we can still use another value for k, which is k equals 0. If that is the case, the summation notation will be changed, and this becomes summation of 1 over 2 raised to k from k equals 0. Then we will subtract 1 from 8, so it becomes 7. And after you replace all the values, their answers will be the same. So that's it for the examples.